All right.
Okay.
Are we?
Yeah.
Are we ready? Okay. Yeah. Sorry for the waiting. So this week we have Kyeongsik Nam from KAIST, who is assistant professor there, and we talk about percolations, right? Random walks, please.
Yeah, thank you for the introduction, and I really appreciate Professor Sang-Imon for the invitation. So this is the second visit for me to I guess here, and the first visit was maybe 2 years ago, so in 2022 maybe. Yeah, and I gave a talk about the random graphs, and today, the object is a bit similar. So the object is also random graph, but I will discuss a little bit different topic, which is called random walk. So today I will talk about the random walk on the percolation. So percolation is all of you have heard about this. So percolation is some kind of random walk, and I'll talk about the random walk on the random graph, which is called percolation. So yeah. So what is a basic graph? So ZD is of course very basic type of graph. And this is very basic question. So let's think about the random walk on the ZD lattice. So this any dimension. So so simple random walk. So we can pick. So we have 2D many neighbors, and we pick any neighbor and we go to that place with the equal probability, and this gives you the simple random walk. And suppose that it starts from the origin. So it gives you, we can think about this object. And many people think about the heat kernel. So what does heat kernel mean? So heat kernel is denoted by P and XY. So what is this? So this is exactly the probability that after n steps, it hits the point Y. So the start, so I will talk about the notation. What does Px mean? So Px means that this is a probability that random, so we think about the random walk starting from X. So X is the starting location. And xn equals y means that after n many steps, the landing location is y. So we can think about this probability, and this probability is called heat kernel. So this is very central object that many probabilists study. And by central limit theorem, we can deduce the very precise asymptotic for the heat kernel. So of course we need to think about the even number of steps, because if we think about 0, 0, so 0, 0 means that we start from the origin and we come back to the origin. So the number of steps should be even. And we can think about such probability. So probability is given by, so it decays like polynomial really fast, and we can precise it under the decay rate. So decay rate is minus d/2. So it depends on the dimension, and this is just simply obtained by the central limit theorem, because central limit theorem says that after n steps, the location of xn is roughly root n. And what is the volume of root n? The volume of root n box is n to the d/2. So we take the inverse. So this gives you n to the minus d/2. So this is quite very classical result. And now this is very standard question. So what happens if we extend ZD to general graph? So if you think about simple random walk on general graph, or possibly this is random graph. So if possibly on the random graph, if we think about the simple random walk, what is the behavior of the heat kernel? So this is quite an elementary question. And today I'll answer to this question. So this is the object we want to study. So this is the heat kernel, and recall that this quantity is what? So this quantity is the probability that the random walk after n steps lands to the particular point, right? So I want to study this probability. And this blue thing is the exponent. So the blue thing is, of course, for the technical reason, we divide by 2, but this blue thing gives you the decay rate for the heat kernel. And it turns out that this exponent is very related to the property of the underlying graph. So this is a volume growth. So in the underlying graph, we think about the radius r ball, and let's count the number of points inside the radius r ball. Then we assume that this is polynomially growing, and so this is called a volume growth. And of course, in the case of lattice, of course, this volume growth is just d dimension. And we saw that in the previous slide, we saw that this heat kernel is also d, n to the minus d/2. So in the case of ZD, they match. Everything is same. So the heat kernel exponent and this underlying dimension, they are same. But it can happen that they are different. So this ZD is very nice. ZD is just lattice is very nice, simple graph. So in that case, volume growth gives you the heat kernel dimension, heat kernel decay. But if graph is fractal, then this is no longer true. Of course, one can ask, what does fractal mean? So I will define it later. Okay. So but this is just rough statement. Okay. Okay. So to compute the heat kernel, it is very important to study the walk dimension. So maybe this is a new notation. So I will define what this means. So walk means that, okay, so we are doing a simple random walk. And walk dimension means that it gives you the location of the random walk after n steps. So after n steps, we assume that the location of the random walk is approximately n to the 1 over this blue thing. Okay? And given this walk dimension, of course, it is hard to compute this. It is very non-trivial to compute this walk dimension. Okay? And in the case of lattice, we can apply the central limit theorem. And in that case, this blue exponent is exactly equal to 2 in the lattice. Okay? And that is called central limit theorem. Okay? And but once we compute this walk dimension, of course, this is hard to compute this. But once we compute this walk dimension, we can automatically get the heat kernel. So we can automatically prove the heat kernel decay. How do we prove this? This is just one-line reasoning. This is very simple reasoning. Why? So after n steps, we know that the location of the random walk is just this. This is the location of the random walk, right? But we assume that volume growth is d volume, right? So we take this power, okay? So we take d volume power. Then the number of possible points that random walk cover is exactly this, right? So this is the number of possible points that random walk covers. Therefore, we take the inverse. Then this gives you the heat kernel. Of course, this is never rigorous because I'm assuming that every heat kernels have the almost same value on the covering points. But that's a bit too much assumption. But assuming this, it's kind of thing, we can roughly obtain this.
Can I ask something? So this size of xn just means that the number of vertices you can visit within.
No, precise. It is a graph distance. So graph distance from the starting point.
So then these are the number of vertices which can be reached by the length and walk, right?
Yes. So the distance from the starting point at the n step after n steps. Yeah. And this is the precise number of points that this random walk can cover. This is because we need to take the power. Yeah. This is radius, and this is volume. Okay. And assuming that every point attains the same similar probability, we can take the inverse. So we get the answer. We get the dichotomy. So if this blue thing is exactly equal to 2, then 2 cancel out. So these two dimensions are same. So as before. In the lattice they are same. Just d, right? But very interesting case is the second case. So second case is today's topic. So second case is when this walk dimension is strictly greater than. So what does this mean? This means that if you look at the first equation, this means that after n steps, the location of the random walk is less than square root of n. Strictly less than square root of n. That is very non-trivial case. And in that case, these two exponents are different. So the heat kernel decay and the volume exponents are different. And this is called subdiffusive behavior of random. So there's terminology. Yeah.
So does this have some sort of hyperbolic nature?
Right. But in the case of hyperbolic, the volume growth is maybe exponential. So maybe, but in some sense, yeah. So in this case, I'm not considering the hyperbolic region, but yeah, because we are assuming the polynomial growth. Yeah. But that's also very natural object that many people study.
So is it not less than 2?
That's also a good question. So of course this may be less than 2, but that's not interesting region, and I don't know the precise example that this is less than 2. That's a bit strange for me. So okay, so in many cases, like lattice and just standard graph, many cases, central limit theorem gives you exactly 2 in many cases, but some exceptional cases, including some fractal property, it is a conjecture that d walk is greater than 2. But yeah, I don't know some precise some concrete example that d is less than 2. That's a bit strange. Yeah. And as I mentioned before, it is extremely hard to prove this thing. Okay, I can give you some concrete example. This one. Yeah. This is fractal, right? So we remove one, we remove. Okay. And we can think about the random walk on this case. Okay, this is a graph. And of course, it is very easy to compute the volume bound. Yeah, so yeah, it's quite easy. We can compute volume bound, but computing walk dimension is a bit hard. But I will just write down the result. So volume growth is just log 3 over log 2. But the walk dimension is log 5 over log 2, which is greater than 2. So this falls into the previous sectors. So walk dimension is strictly greater than 2.
Does the starting position independent?
Which one is independent?
Starting position of walk does not.
That's also a good point, but in this case, not independent. Yeah, it is independent. Yeah. So in many cases, yeah, of course, this graph is not symmetric, but yeah, it is. In this case, it is independent. But also in many cases, everything is independent of the starting. Yeah.
So what is the edge in this graph?
So this, the vertices and edge.
Can I compare a little bit? So what's the difference between volume and the work?
Oh, volume is quite simple. Volume is just, we think about the graph distance r, and we count the number of points inside the ball. Okay, that's the volume growth. And walk division is very different, maybe different from the, it is independent from the volume bound. So this is the typical location of the random walk from the origin. So for example, in the case of ZD, so this is ZD. In the case of ZD, this dimension depends on the underlying dimension, but walk dimension is always 2, independent of D. Yeah. This is always 2. Yeah. This number is always 2, regardless of D. For example, if you think about the random walk on the cube, the 3-dimensional cube, it is also 2. Walk dimension is also 2, in any dimension.
Maybe I missed the definition of the cardinality of that thing, or
Sorry. So maybe this is a bit misleading. So yeah. So yeah, we have the ZD lattice. So we have ZD lattice, and this is origin. And after we do some simple random walk here, and suppose that this is a location at xn. Okay, and that notation is that it is a graph distance from the origin. Graph distance. So typically, graph distance.
I
Yeah.
see. So that
This is root n, regardless of dimension.
you're talking about the distance between 0.
0 and right. Starting point and landing point. Okay, so there's a dichotomy. Okay, and this is example. Yeah. So this is fractal case, which gives you.
So sorry, just to check that I have it the right one. So if in a hyperbolic graph, it's very hard to come back to the origin. So
right.
The walk dimension would be
Will be very large. So it tends to maybe exit. So
should
maybe
be very small. The distance will be almost
large. Okay. So sorry. So I'm not very familiar with hyperbolic graph. So maybe
I say an infinite tree.
Infinite tree. Yeah.
You're almost always going to end up at distance n.
Okay. In that case, it is. It more tends to the infinity. So in that case, I think the location of the random walk is much far away from than the standard
So
case.
that means walk dimension is smaller than 2.
Small.
Right?
It can be smaller.
And here
you're
you
right.
want the opposite. You want that it's easier than usual to come back to the origin.
Yeah.
Okay,
You're right.
thank you.
Good. Yeah. Thank you for the point. Yeah.
Thank you
You're
very
right. Mhm. Yeah. Right. So the regular tree is very nice example. Yeah. Thank you. There's a positive drift to exit. So in that case, maybe I believe in that case this dimension is 1 because there is a linear drift. It is a positive drift towards to the descendant. So maybe this one. Yeah. Thank you. Okay. Okay. So this is a big conjecture. But this is not rigorous. So these two people are maybe physicists, and in maybe 40 years ago, this is not mathematical journal, so this is physics journal. So in the physics journal, they made a conjecture. So they conjectured that on a large class of fractal graphs, we have a universal heat kernel. So regardless of the dimension of the graph, the heat kernel should decay like n to the minus 2/3. But this is not rigorous in the following sense. So they didn't mention for which kind of graphs this conjecture is true. So this is just physics paper, and so they just give some heuristic. Okay. And but it's surprising in the sense that this exponent does not depend on the particular structure of graph. This is quite universal. So that is their conjecture. Yeah. It never depends on the underlying dimension and nothing. Yeah, nothing else. Okay, so this is 40 years back to conjecture, and okay, I'll give you a very simple case. Okay, so this is a bit similar to what he mentioned about the infinite regular tree, but it is a bit different. Okay, so I'll talk about what this means. So every person has some random number of descendants. So in this case, the top person has three descendants, and this is just random number. For example, the second one does not have any descendants, so it can have 0. But it can be very large, 5, okay? So this is some random number of vertices. And the critical thing is that the expected number of descendants is exactly equal to 1. So what does critical mean? So if this average number is less than 1, then this tree dies out. So this tree will vanish. But if this is greater than 1, then this will survive with positive property. Okay, so there is some kind of threshold that phase change happens. Okay, so such threshold is exactly the average number of descendants is 1. But in this case, we have a very bad situation in the sense that with property 1, this society will die, eventually extinct. But of course, there is a very special case that every person has number 1 descendant. So 1, 1, 1, 1, 1. In that case, this society will survive, but that's very exceptional case, and I will not think about that trivial case. So except this trivial case, one can show that if every person has average number of descendants 1, this society will die. This is known fact. Okay. Okay, but let's think about the 0 probability. So let's condition this society on the non-extinction. Of course, this is very strange because this is 0 probability. So we cannot condition, right? So for example, what is the conditional property that we learned in the high school? So AB is property A intersection B divided by property of B, but we cannot do this conditioning if denominator is 0. This is not well defined. Okay, so we cannot define conditional property, but mathematically we can rigorously define this by taking the limit of the final limit. Okay, so after this some rigorous thing, KAIST proved very nice result. So this is just 2 years after the previous conjecture. So it was 84, okay, conjecture. But after 2 years, he solved this for this graph. So conditioned on this very strange 0 property event, he showed that this conjecture is true, n to the minus 2/3. Yeah. Moreover, he deduced very precise exponent. Walk dimension 3, volume dimension 2. He did more.
For this particular tree.
Very particular tree. Yeah. Conditioned on non-extinction. Yeah. So this is very fundamental result. Okay. Next. Okay, now people have changed the direction. So of course this is very particular case of graph because this is just tree. There's no loop, so everything becomes very simple. But we can think about non-trivial graph like percolation on ZD. So what is percolation? So percolation means that in the lattice, every edge is open with property P, okay, and everything is independent. So for certain P, for example, we can get this sample, right? So some edges are closed and some edges survives, right? So this gives us a random graph. This is random graph. And of course, there are some loops, right? There are some loops. Okay. And it is known that there's a phase transition value. So it is called PC. So C denotes the critical. Okay. So this means that if P is less than that threshold, there are only few edges, right? There are only few edges. That means that there is no infinite size cluster. Okay. But if P is above the value, then there are many edges, so that there is infinite cluster. Okay. So there is certain kind of threshold. Okay. Which is called PC. Of course, computing this PC is very hard.
What happens if the P is exactly PC?
That's also a very important question. So that is written in the next slide. So, yeah. That is indeed very important question in probability theory. Okay, so if P is above this PC, so this means that P large means that there are many edges. So it behaves like standard lattice, right? Because there are too many edges. So in that case, it is a classical result that the heat kernel is very similar to the just lattice case. So Gaussian is lattice case. Okay, so if P is greater than PC, then it behaves as if P equals 1. Okay? But question is critical case. So what happens if P is exactly the same as PC? That's very hard because first we don't know the value of PC. Okay, that's very abstract number, and yeah, something can be mixture. So very delicate. So there's many issues. But the first issue is that it is not known whether infinite cluster exists or not. We just know that if P is smaller, then there's no. If P is large, then there is. But at this exact value, we don't know. Nobody knows answer. No. But we expect that if exists. Okay, so I write down this if because I don't know the answer. If exists, then we expect that the infinite cluster looks like fractal because P equals PC means that it is some kind of intermediate value. So the graph will behave very differently from the lattice. But this is just rough sense. Yeah. I don't know how to make this rigorous. Yeah. Okay, but something is known. Luckily, something is known that if dimension is 2 or greater than 6, there is no cluster at the critical point. So 6 is critical. So somebody calls 19, but but I don't want to get into details. But yeah, you can regard 6 is upper critical dimension. So either dimension is small or large, it is known that there is no cluster. Okay? But between 2 and 6, nobody knows. It is a big conjecture. So we can think about the conditioning. So as I mentioned before, this is the zero property event, right? So there is no infinite cluster, so it is zero property event. So this is not well defined. So we can think about the rigorous limit. So we can think about the finite level and we can take the limit. Okay, so this is one rigorous way to think about this limit. And as I mentioned before, it is very non-trivial to show that this limit exists. Okay, but once we assume that limit exists, the same person, so Keston, so this is a person who worked with a tree. The same person showed that in the case of 2D, the distance, the location of the random walk is strictly less than square root of n. So it is very different from the standard random walk, because in the case of standard random walk, location is root n. But in the case of critical one, the location becomes strictly less than root n. So he proved the existence of constant epsilon such that this is true. Of course, computing the value of epsilon is very hard. Nobody has asymptotic now. It is only known that epsilon is positive. So indeed, if one can prove the exact exponent, then that will be a very surprising result.
I'm a bit confused. So you have 2D. So this
Dimension is 2. Dimension 2. Yeah.
But you also said that there's no infinite cluster when these two.
No, there's no cluster. No cluster, but we can condition on this zero property then. So this is a bit we cannot think about it because this is a bit very abstract.
I see. No infinite cluster without, or I mean that's almost surely, right? So
so it is zero property.
Zero
Infinite
property.
cluster,
Okay.
So this kind of very singular events makes this graph very fractal, very different from the original graph. Yeah, and this is the result for 2D. Okay. And as I mentioned before, 6 is a bit interesting. 6. Okay. Okay, yeah, I'm not. So, okay, so I'm writing down this conjecture one more time. So, 40 years before, Alexander and Orbach conjectured that. So they considered this. Okay, so don't write this IIC. IIC means that IIC this. So it is called incipient infinite cluster. So this is the conditioned on infinite cluster. Okay, so we are assuming the zero property event that infinite cluster exists, and on that event they conjecture that this is true, but this is wrong. Many people believe that this is wrong in the sense that this will be false when dimension is less than 6, and there are many. Yes, so this is widely believed, but of course this is not proved yet. But many mathematicians believe that this will be false when dimension is less than 6, and the surprising result was proved in 15 years ago. These two people show that if dimension is greater than 6, then this is true. Okay. So if dimension is above 6, they prove that the random walk on the infinite cluster has this heat kernel, and this exponent does not depend on the dimension. It is universal result. Okay. So far I talked about I talked about the two models. So the first model is a tree. So tree is easier because there's no loop. Everything is simple. But a bit more complicated model is percolation, which has many trees. So it took, how many years it takes? So this, in the case of tree, it was proved in 86. So, but in the case of percolation, when is it proved? So it is proved in 2009. So it took 25 years to extend from tree to lattice, right? So it took so many years. And also, many people are considering the dependent percolation. So we remove the independent thing, right? So in the case of percolation, every edge is independent. But how can we remove that? Let's remove that. So this is the very famous voter model. So vote means we are voting to some person, right? In the politics, right? So so there's a red thing, red and blue, right? So there are two politics, opinions, right? But we are staying in the society, so we are not independent from other persons. So somebody's opinion affects others, right? So suppose that in the society every person is vertex and some persons are connected by edge. Then with some property somebody affects the other, right? So voter model is mathematical rigorous model. So this is some kind of Markov chain. This is some kind of Markov chain interacting particle system, and given graph, somebody affects the neighbors with some property. And this is the precise Markov chain, and one can define this. And it turns out that, of course, this is never independent because there are so many interactions by edges. And in some sense, this has some decay, right? Polynomial decay. And this is very different from independent case in the sense that if you take the summation of this correlation, it becomes infinity. So you cannot ignore the dependence between several people. Okay, so this is called the voter model. And the next model, the blue thing, is called the Gaussian free field, and this is today's topic. Okay, so today I will not talk about the voter model. Instead, I will talk about the Gaussian free field. Okay, so this is just that one slide. This is definition. This is very simple, right? So Gaussian free field is just random height function. So at every lattice, you are given a random height. So for example, if you think about this point, this attains very high, very large height, but this is very large, this is very small height, right? So every point, there is a random height assigned, okay? But the heights are not independent, so they have some correlation. So how does the correlation decay? Okay, so how does correlation decay? Polynomial decay. So this means that if you pick 2 points which are very close to each other, then correlation is quite large. Correlation is quite large, so their heights are they are related to each other. But if you pick 2 points which are very far away, then this correlation is zero, almost zero, right? Therefore, these two heights are quite independent. So this is the model that Gaussian free field is a model that the correlation of two heights at locations decay polynomially fast, and the decay rate is 2 minus d. So 2 minus, of course, 2 minus d is very natural because this comes from the PD. So this is a green function in PD. So this is the fundamental solution of the Laplacian, and in that case, this is exactly the asymptotic of the fundamental solution. So this is quite physically natural exponent, 2 minus d. Okay, now we can similarly define the level set. Level set. So we collect the point whose height is above some number. Okay, we pick some collection of the points, random points. These are random points, right? Because heights are random. Okay. So this is of course dependent model because every points have some correlation. This is dependent model. Okay. Now we can also think about the critical threshold. So if h is small, what does h small mean? H small means that there should be many points, level set. There should be many points. Therefore, it should have infinite cluster. Whereas if this number is very large, then it is unlikely that point is included here. So there are only few points here. Therefore, there is no cluster. Okay, so there should be some dichotomy. If h is small, there are too many points. Therefore, there should be infinite cluster. Whereas, if h is large, there are only few points. Therefore, there should be no cluster. There's a dichotomy. And this is very important, and this is also physically very important question. And people have studied this question a lot. This also has very long history. Because this model is quite important in statistical mechanics. But this gives you some kind of random graph, right? Random graph, which is a subset of ZD. Okay. Okay, this is a result. 3 result. This is up to date. 1987. This threshold is non-negative. Okay. And okay, so this is non-trivial. H star is finite. This is very non-trivial because okay, so what does it mean that H star is infinity? H star equals infinity means that okay, so what does this equals infinity? H star infinity means that for any value h, this is connected. So but it's a bit strange, right? If h is large, then there should be only few points. So why do we expect there is an infinite cluster? But proving this is very hard. Reversal is very hard because of the correlation, because of the positive correlation. So if something is large, okay, so there's a plane. If something is large, then by positive correlation, neighbors should be always large. Large. If something is large, everything is large here. So it is a very tricky to prove that H star is finite. So it took almost 25 years to prove this. Yeah. It's very hard, very non-trivial that H star is finite. Okay? And also it is more difficult to remove zero condition. So in 6 years ago, they proved that H star is positive. Of course, computing this value, exact value is impossible. Yeah. We just know that H star is strictly positive and finite. We just know this. This is the most recent result. Okay.
But H star depends on D, right?
Exactly. That's right. Yeah. Okay. But okay, so this is a bit trick. Okay, so originally we are considering the lattice, right? We are considering the lattice, but people have tried to overcome this difficulty because nobody could precisely compute this H star, right? But so this is a reason. The reason is that the model is quite complicated. But people think about the interpolation. So given the graph, they take the interpolation. Okay? This is continuous graph. Continuous graph. And then we can similarly define the continuous model on this graph. And in this case, luckily, people could prove that H star is 0 in the continuous case. So if you make discrete graph to continuous graph, then the model becomes integrable so that we can compute h star. So for any dimension, value is h star is it. This is for the continuous graph, continuous, not discrete. In the discrete, nobody knows. But in the case of continuous case, in 8 years ago, he loop proved h star is 0. And also, at this critical level, this has no infinite cluster. This has no infinite cluster. Okay, and yeah, okay, so now it's time for me to talk about my main result now. Okay, so here, yeah, because we have some understanding, right? So we have some understanding that in the case of critical case, yeah, continuous case, we know the exact value of critical level, and yeah, it does not percolate. And then we can also think about the random walk on the critical set. And recently we showed that the conjecture is true. So it does not depend on the dimension, but regardless of dimension, in this model, heat kernel decay is like n to the minus 2/3. But the drawback is dimension should be greater than 20. So this is the drawback of our result, because we expect that this is true for b greater than 6. So that's one drawback, but this is the first result. This is the first rigorous result of this conjecture for dependent model. Okay. So yeah, so I will just give a very short overview of this object. Okay, so yeah, this is the very basic inequality that we use. So I can draw a picture. Maybe some of you know this, but okay, so okay, so we are given 4 points, 1, 2, 1, 2. Okay, and suppose that A is the event that x1 is connected to y1. Okay, and B is the event that x2 is connected to y2. Okay. So we have these two events, and what does so these two are not independent. They depend. Okay, they are not independent, right? Not independent. Okay? Not independent. Yeah, they can interact because they can share some edges, right? They can interact. But FKG inequality says that. Okay, so in the case of independent case, the intersection property is just product. They are equality, right? But FKG says that they are positively correlated. They are positive correlated. Okay, so this is called FKG. So intersection property should be always greater than product. Okay, they are not independent but positive correlation. And BK inequality is So this circle notation. So what does that mean? Circle notation is that A circle B means that they are disjoint occurrence. So disjoint means that x1 is connected to y1 and x2 connected to y2 using different edges. Okay, so if you draw this, then we get this situation. So they do not share the path. This and this, they don't share. Yeah. So if we put this different edges condition, then this property is smaller. Okay. Yeah. So this is called BK. So in this kind of percolation theory setting, it is very useful to use these two inequalities. So the first thing is the positive correlation result for the monotone event, and second is the disjoint for the disjoint occurrence. So this is the disjoint occurrence, this is the BK inequality, and this is FKJ. FKJ we allow they share edges. We allow. So this is greater, and this is the smallest one. Okay, now this is a way to obtain the heat kernel. So so this gives you the very general formulation to study the heat kernel. So maybe All of you have seen this when you're a middle school student. So this, yeah. So we have a resistance on the edge, and then when I was middle school student, there are some questions that what is the effective resistance between these 2 points, right? This very basic question, right? So and maybe everyone knows that if there are 2 resistors here, and this is 3 and this is 5, then this should be 8. And if this one is 1, and this one is also 1, then this gives you 1/2, right? So this is summation, and this is reciprocal, okay? Yeah, so like this. So for any graph, so any given graph with unit resistance, we can compute the effective resistance between 2 vertices, okay? So this is called effective resistance of the graph, okay? And this surprising result says that if we know the volume growth, of the graph and the estimate for the effective resistance, then we automatically get heat. Of course, these 2 numbers are not special. So so you can change the exponent here. So you can change exponent, and of course you will get different one. But the important message here is that given the volume growth and effective resistance bound, then you get heat flow.
So what is this notation? Resistance?
Oh yeah, okay, that's a good point. So that means that it is a resistance between the origin and the radius r ball, sphere.
Oh.
Yeah. So graph here, so we have radius r ball with this sphere, and what is the effective resistance between these 2 sets?
So in the sense you identify all the vertices on the ball, the
Ah.
boundary.
We are not okay, so we can similarly define the resistance between 2 sets. That's possible. Yeah, we are not exactly identifying them as a point, but yeah, we can similarly define it, and yeah, this gives you Okay, so this is very surprising result. Okay, so but okay. Number 1 is quite straightforward because for given graph, we know how to understand the volume growth. So number 1 is a bit familiar for us, right? What is non-trivial thing is number 2. So how can we compute the effective resistance? It is a bit non-trivial. How do you compute this for general graph? Of course, for this kind of very simple graph, we know how to do it. But how do we compute resistance for this graph? So this is the general strategy. So this is the notion of cut set. So maybe everyone knows, but let's quickly review this. So cut set is that, okay, so suppose that we want to compute the resistance between this point and the top point. Cut set is that after removal, 2 points are not connected. So these four edges are cut set, right? After removal, disconnected. And the very famous inequality, which is called Nash-Williams inequality, says that if we are given some collection of disjoint cut sets, then we can lower bound the resistance. So resistance is lower bounded by summation of 1 over size of cut set.
So the concept of resistance you explained over there. So how do you associate a number with the edges?
Number with
So how do you define the resistance?
so every resistance value is 1.
Okay.
Every edge is 1. Yeah, everything is 1. So this estimate depends on the structure of the graph.
Okay.
Yeah.
Right. So I see.
Yeah.
So between the resistance, you are
Mhm.
getting the minimum value when the value is computed with that strategy.
Sorry, so minimum value of what?
Minimum value. Minimum resistance between D and W, where the resistance is computed over the cut.
You mean this right hand side?
Yeah.
Okay, so here we are fixing 2 points B and W, and there may be several choices of the cut sets, right? So this lemma says that if one can choose some nice cut sets which are disjoint. Okay, so this pi ends are all disjoint. Okay. For any such collection, this deterministic inequality is true. For any such collection. So there are so many ways to construct these cut sets, but regardless of cut sets, this inequality is always true. Okay. So so this is quite straightforward if you think about this Okay, so how do I do English? This is 직렬병렬. Okay, so I don't.
Series or
parallel,
parallel?
serial parallel.
Right, right. This is series parallel. Yeah, thank you. Yeah. So this summation is series, and this reciprocal is parallel. Okay, because so if drawing that, so yeah. Okay, so we have right here. Okay, so for example, let's draw let's think about the South Korea. So this is Seoul. Yeah, and this is Busan. Yeah, so every city is just vertex. Okay, and we say that H is two vertices are connected if there's a road between them. Okay, so there are several ways to Okay. There are several highways. Okay. Okay, so some of them right. So this graph, Seoul to Busan. I want to prove the effective resistance between Seoul and Busan. How do we lower bound it? We want to get so it is it will help us if so in other words resistance will be small if there are many roads. Okay, so if there are many roads here, then resistance will be smaller, right? There are so many ways to go to Busan, right? So if this size is larger, then resistance will be smaller, right? This is called parallel law. If you have k many parallel things, you get 1 over k, right? You get reciprocal. So this is parallel. And this gives you 1 over pi n, okay? And this length, the length between Seoul and Busan. So if the distance between Seoul and Busan will be larger, then resistance will be larger. It's quite straightforward. This is called series rule. Okay? This is called the series rule. Just we take the linear summation, right? We take linear summation. 3 plus 5 is 8. We are taking the summation of this, right? Summation of this. So this right-hand side is just combination of parallel law and series law. And the key point here is that this is true for any graph. So of course, everything is simple here because there's no, so everything looks like tree, there's no loop, but this Nash-Williams equality says that for any graph, including many loops, this is always true. Okay? So this is a very useful way to lower bound the resistance. And once you get the resistance, then you can compute the heat kernel by this theorem. So this is a broad strategy to prove the heat kernel. Okay? So for the volume growth, so we are very familiar with volume growth, so we can escape this. And for the resistance, our goal is how to construct constant. This is our goal, right? So I think now it's a bit too complicated. So so this is almost last slide. So this gives you how to construct constant. Yeah, maybe this picture will be enough. So let's go from here to there. Okay? So this is the origin, this is the starting point, and our goal is I want to reach top line. Okay? Lane. So this lane is that. Okay, so there may be some paths, but it can have backtracking. So they backtrack means that. So I want to go from here to here, and I want to, so how do I go from here to there? Here, okay? There are some backtrack, there can be some backtrack. But lane means that this is the last backtrack. So for example, let's assume that J is this one. So this is level J. What is a lane? Lane is maybe this lane. Because after this point, it does not go back to this level, okay? Because this has a backtrack, right? Backtrack. So we take the last backtrack, okay? And one can prove that for any graph, such collection of lanes is always constant. So once you can find once you can understand the collection of lanes, then you can understand the cut set, and therefore you can apply Nash-Williams inequality. Then you get the estimate for the resistance. So this is a broad strategy. Okay. Yeah. So this is one. So this applies to any graph. For any graph, once you take the J lane, this lane, then that is concept. Okay, now I think this is too technical, so I want to skip this. Yeah, that's for today. Thank you.
I mean, you actually started a bit late, so you had time. But anyway, any questions?
Yeah.
Is the number 20 related to how you make the J lane, how you make the cassette?
Yes, that's the technical point. So of course I believe that dimension should be great. I believe that this can be replaced by 6, but we failed to it. The reason is that when we construct this J lane, there are some difficulties.
Then maybe if we construct a better cassette,
Then
use
we
the
can
same
upgrade.
strategy.
Yeah, that's right.
Do you think that this is false when D is small enough?
I believe this is false when dimension is 3, 4, 5, 6. 3, 4, 5, 6.
And also about the earlier conjecture, discrete case. So what is the belief for the exact when D is exactly 6?
Nobody knows. If dimension is 6, then some people expect that there is a log correction, but nobody knows. That's very delicate. Maybe I believe there is a log correction, but yeah, people don't know.
Why people believe the 6 is magic number? Is there any experimental result or some?
There is a mathematical reason. Okay, so I can talk about this. So so why is 6 special? So this is just one line inequality. So we have this decay, right? So let's write that decay. Decay. So what is a basic case? So we always know that base case is tree. So tree means that there's no loop. What is a simplest loop? Simplest loop is triangle. So let's think about the triangle. X, Y, Z. Okay, so let's compute such property. So what's the property? Okay, so let's count the number of such triangles. So we need to take the summation. Okay, so and of course let's pick the point here, 0. Okay. Okay. Yeah, we have such object over all xy. So this is some kind of expected, not exact, but some kind of expected number of triangles including origin. Okay, so this is finite if and only if dimension is greater than 6. So this means that 6 is critical dimension in the sense that above dimension 6, the critical percolation does not have a loop in some sense, in some very weak sense. But if dimension is less than 6, then there are lots of possibilities that graph contains many loops. So that's the reason why 6 is very important.
So it might be a silly question. So at the beginning, you compared the heat kernel to the dimension you define with the volume. And I was wondering if there are some other notions of dimension which could be interesting.
Here, okay, so heat current volume, yeah, okay.
I think there's a very famous one which is called asymptotic dimension. I'm not sure if there are any results about that.
Asymptotic dimension of the graph?
Yes.
How is it defined?
Okay, the definition is a bit
sorry, I don't know about that. Yeah. So you want some relation between that notion?
No, I was just wondering in general if this kind of question has also been studied with other notion of dimension than the volume.
Yeah, I'm not sure about that. Yeah.
Okay. Thank you.
Yeah, let's talk about that dimension. Yeah.
So it's always about the lattice points, right? When you take these graphs, that is G to the D and then.
Yeah, it is always a lattice.
Yeah.
Yeah.
But what if you change the underlying lattice to the?
That's also very interesting. So for example, if you think about the percolation on general graph, then that's also a very natural object. So, but yeah, of course this is basic case. So yeah, people.
Like hexagonal grid or triangular grid.
Ah, yeah.
Or these things.
That's very hard. So yeah. But in the planar case, hexagonal thing and everything is planar. So in that case, I believe it behaves like Z2. But in the higher dimension, I think the general belief is that the percolation on graph depends on the structure of graph. Or many people also think about the percolation of the group, and so that's also very delicate. And yeah, so one can also ask some similar questions about the percolation of general graph or general group. That's also very nice question.
But sorry, if you take the regular grid or the triangular grid,
Triangle grid, yeah.
you can get both of them from the same group, right?
Same what?
You can get them from the same group. I wonder if there might be a result which is if you can get the two graphs from the same group, then the percolation will be sort of the same. And maybe that's not true at all.
So if you change like triangle lattice, then okay. So for example, like hexagonal thing, the value of PC is also 1/2. But the studying the critical behavior can depend on which graph we pick. So
Okay.
like hexagonal graph, triangle graph,
That's
square
okay.
graph. So everything requires some different strategies. So yeah, I'm not sure. Yeah, what happens there. Yeah.
Right. Any other questions? Oh yeah.
So how good is this Nash-Williams bound for the effective resistance? Like, is it?
Oh yeah, that's
It's a
very
lower
good
bound,
point.
but is it can be?
It is very sharp. So once you choose this concept very nicely, then this gives a very strong bound.
But do you mean that you have always equality for certain collection of disjoint concept, or it just means
For nice graph, this can attain equality, but for general graph including so many loops, then of course they don't match in general. But if you choose concept very nicely, then this already gives you very nice one.
right? Any more questions? So if that, let's thank the speaker.
Yeah.